Hello, my name is Richard Novickis and I am a researcher at the Institute of Electronics and Computer Science in Latvia, more commonly recognized as EDI. Today I will present our main contributions in the PRYSTINE project. The slide shows EDI drive-by-wire car demonstrator, which was used as a base for carrying out our research. EDI has developed an overall architecture of the fail operational embedded intelligence platform that executes artificial intelligence-based algorithms for sensor data fusion, object detection, classification, while simultaneously being fail-safe and fail-operational. As a base for our platform, we adopted a mixed criticality approach that integrates safety and high-performance controllers. In this particular case, the safety controller is based on an Infineon RX 3-core microcontroller, while the high-performance computing is left to NVIDIA's PX2 platform. The role of the safety controller is to monitor the operation of the high-performance controller and to do some basic collision avoidance by fusing data from radar and LiDAR. On the right side you can see safety controller's operation during a pedestrian crossing test. As for the high-performance controller, we have chosen the NVIDIA's PX2 platform. Here you can see the initially envisioned functional architecture of software running on the controller. The next challenge for the high-performance controller was the implementation of the functional architecture in a comprehensive way suitable for exploration. This has been achieved by designing modular frameworks for system architecture implementation that follows the blackboard programming pattern. We have used the frameworks to implement system architecture, and here, for example, you can see object detection and mapping subsystem of the EDI drive-by-wire car. Note that here every box represents a COM-page component, or you could say a thread or a process. This system can be easily extended to multiple platforms or multiple computers. It doesn't matter. During the project, together with our partners, we have derived a range of requirements and scenarios for EDI drive-by-wire car demonstrator. Most importantly, there are the KPIs, which include the successful execution of the scenarios with injected artificial failures, such as sensor connection interruption, distortion of camera images, etc. And the ability of the system to detect sensor failures and faulty components by utilizing supervisor, artificial neural network, and distributed architecture. Further, I have a video demonstration of the car executing these defined scenarios, which I would like to show you right now. The EDI drive-by-wire car demonstrator had to meet 100 technical requirements and demonstrate them in 19 scenarios. Here you can see our particular setup when developing the autonomous vehicle. So this is a particular hardware-in-loop setup where actually we call it a car in the loop. Here you can see the EDI drive-by-wire car system, which actually allows us to give commands to the vehicle. Yes. So in essence, the vehicle is actually driving in the simulator. Yes, and all the control signals are applied to the car in real time. So for this setup we don't require the safety driver. And you can see that actually the high performance and safety controllers are in the car while in the test. So first of all, we have implemented automatic mode. Yes. In this mode the control is given back to the car, so to speak. But still the safety driver has to sit in the car due to legislation and safety reasons. So to exit the automatic mode, the driver either presses a big red button or just starts driving the car. Here you can see car doing a left turn while the pedestrian is on the road. So the car stops when it meets the pedestrian. To achieve this, we used multiple artificial intelligence-based and conventional approaches. So first of all, we used inverse perspective mapping. Yes, then we used different deep neural network-based object detectors and classifiers. Yes, for image data and LiDAR data. And this further was fed into trajectory planning software, which basically allowed the car to do these scenarios autonomously. The vehicle is able to deploy emergency braking if there is a risk of impact. In fact, here we demonstrate the functionality of the safety controller. So the safety controller uses data from radar and LiDAR. So radar does onboard processing by itself, but AURIX is actually powerful enough to analyze the data from a LiDAR in real time. And you can see if the pedestrian is removed or it goes away, the car can continue the trajectory, executing that trajectory. So this is one of the scenarios. Further, the safety controller has a safety mechanism which is based on heartbeats. So the high performance controller has to send heartbeats all the time. And here AURIX actually detects that these heartbeats are absent and it safely stops the car. So that's about it for our demonstration. Thank you very much for your attention, and I'm open to questions. Thank you.